Sanford Underground Research Facility, or SURF, is America's deep underground science laboratory. Our mission is to advance world-class science and inspire learning across generations. SURF hosts cutting-edge research in multiple disciplines, including physics, geology, biology, engineering, and more. Work at SURF is contributing to the fundamental understanding of our universe, advancing our nation's energy independence, exploring life in extreme environments, and providing basic research that is the foundation for ongoing technological advancement around the world. SURF's collaborators include over 2,000 scientists from more than 200 national laboratories, institutions, and universities worldwide. SURF also plays a vital role in inspiring the next generation of STEM professionals with a robust education and outreach program that reaches nearly 20,000 students and 400 teachers annually. SURF is generating a $2 billion economic impact on South Dakota this decade alone, with the potential to create 1,200 jobs across the state. We are proud of our history, which includes Nobel Prize-winning research on this site, and we have a bright future with ongoing and planned experiments that will continue to inspire and push the boundaries of human knowledge for decades to come. The Sanford Underground Research Facility, or SURF, is America's deep underground science laboratory. Our mission is to advance world-class science and inspire learning across generations. SURF hosts cutting-edge research in multiple disciplines, including physics, geology, biology, engineering, and more. Work at SURF is contributing to the fundamental understanding of our universe, advancing our nation's energy independence, exploring life in extreme environments, and providing basic research that is the foundation for ongoing technological advancement around the world. SURF's collaborators include over 2,000 scientists from more than 200 national and universities worldwide. SURF also plays a vital role in inspiring the next generation of STEM professionals with a robust education and outreach program that reaches nearly 20,000 students and 400 teachers annually. SURF is generating a $2 billion economic impact on South Dakota this decade alone, with the potential to create 1,200 jobs across the state. We are proud of our history, which includes Nobel Prize-winning research on this site, and we have a bright future with ongoing and planned experiments that will continue to inspire and push the boundaries of human knowledge for decades to come. The Sanford Underground Research Facility, or SURF, is America's deep underground science laboratory. Our mission is to advance world-class science and inspire learning across generations. SURF hosts cutting-edge research in multiple disciplines, including physics, geology, biology, engineering, and more. Work at SURF is contributing to the fundamental understanding of our universe, advancing our nation's energy independence, exploring life in extreme environments, and providing basic research that is the foundation for ongoing technological advancement around the world. SURF's collaborators include over 2,000 scientists from more than 200 national laboratories, institutions, and universities worldwide. SURF also plays a vital role in inspiring the next generation of STEM professionals with a robust education and outreach program that reaches nearly 20,000 students and 400 teachers annually. SURF is generating a $2 billion economic impact on South Dakota this decade alone, with the potential to create 1,200 jobs across the state. We are proud of our history, which includes Nobel Prize-winning research on this site, and we have a bright future with ongoing and planned experiments that will continue to inspire and push the boundaries of human knowledge for decades to come. The Sanford Underground Research Facility, or SURF, is America's deep underground science laboratory. Our mission is to advance world-class science and inspire learning across generations. SURF hosts cutting-edge research in multiple disciplines, including physics, geology, biology, engineering, and more. Work at SURF is contributing to the fundamental understanding of our universe, advancing our nation's energy independence, exploring life in extreme environments, and providing basic research that is the foundation for ongoing technological advancement around the world. SURF's collaborators include over 2,000 scientists from more than 200 national laboratories, institutions, and universities worldwide. SURF also plays a vital role in inspiring the next generation of STEM professionals with a robust education and outreach program that reaches nearly 20,000 students and 400 teachers annually. SURF is generating a $2 billion economic impact on South Dakota this decade alone, with the potential to create 1,200 jobs across the state. We are proud of our history, which includes Nobel Prize-winning research on this site, and we have a bright future with ongoing and planned experiments that will continue to inspire and push the boundaries of human knowledge for decades to come. Turn it over to our panel very shortly. Tonight,
for the inaugural edition of Deep Talks, we're celebrating Dark Matter Day. And this is part of a global celebration. So we are taking part in the same sort of events that are happening around the world this time of year here at the end of October, whether that be at CERN in Europe or KEK in Japan or at national labs and universities all around the country. So we're all taking part in this celebration of the great work that's done by some of the folks here at this table. So it's a great night to be able to celebrate these things. We're going to hear a lot more about it very soon. But first, we need to thank the awesome people who make this possible. That wonderful food and beverages we just got to enjoy, and this event is thanks to our sponsors. And to thank our sponsors properly, Michelle Kane with the Surf Foundation is here to do that.
Thanks, Mike. Okay, who did I give the little mountain goat to, or the bighorn sheep to? The stickers? These are our new people, our first timers. So thank you all for joining us. And we wanted to do something fun. So whether you're here in person or online, we are just very glad that you're here. As Mike said, my name is Michelle Kane, and I'm the Donor Relations Manager with the Surf Foundation. And the Surf Foundation, what we do is we raise funds for outreach programs like we're doing here tonight, for internships, for teacher development, STEM education, cultural programs, and building an intellectual community. You hear that term a lot at SURF, and that's under our Institute for Underground Science. And you're all part of this intellectual community. In fact, after the session tonight with this amazing panel, all of your IQs are gonna be like +5 points right here when you're walking out. And we want you to go out and tell everyone what we're doing here at SURF. So we are deeply grateful for tonight's sponsors. And it's their generosity that makes events like this possible. And that includes Chris Mitchell from Edward Jones and Spearfish, Chuck and Jolene Linkton-Wallner, loyal supporters of Deep Talk since 2019, and a special thank you and cheers to our friends at Crow Peak Brewing and Spearfish who have quenched our thirst for Deep Talks since 2015. And I think when I checked everyone in, if you're out in Spearfish and you go to Crow Peak, can you thank them for supporting science and make sure that you really see them and that they feel recognized? So if you're attending Deep Talks tonight and you'd like to support our program, well, you can do that too. We have a Surf Foundation donation box in the Visitor Center, or you can join us online. These contributions help fuel our quest for knowledge and to help support our outreach events. So thank you for being part of our mission, and we're excited you're here. Back to Mike.
Thanks so much, Michelle. Well, tonight, as you see, we're going to hear about a day in the life of a dark matter scientist. And these four folks up here are four of a large team of people who make Lux Zeppelin, the world's leading dark matter experiment, happen every day. Keeping a dark matter experiment going a mile underground at SURF is no small task, and we're going to hear more about that. And again, this is part of that celebration of a Dark Matter Day. I'm just going to give a quick introduction. At the end, we have Julia Delgado, who's an engineer and experiment scientist at SURF. Charles Maupin is a mechanical engineer here at SURF. He's been instrumental in both the setup of LZ and the ongoing effort to run this experiment. He has a great understanding of the history of this awesome experiment. Olivia Valentino is a second-year PhD student from Italy, studying particle physics at Imperial College London. Did I get that right? Thank you. And Chad Dunbar is a mechanical engineer here at SURF, who is among, again, that staff who keep LZ running every day. And with that, I'm going to turn it over to the experts and welcome everyone here.
The bottom line is we really don't know, and it's why we're studying it. So we know that it's there because when we look at the universe, there's a series of things that we don't really know how to explain. We know certain laws of physics, but if we look up there, for example, one of the main examples is that when we look at galaxies, we see them spinning faster than they should do. So we know that there's a certain amount of matter, which is stars and planets, but if we only account for that, they're going too fast. So we know that there's something there that's massive and it's just making them spin faster. And so we kind of know that we have to look for this. And in particular, studies have shown that actually dark matter, which is how we call this extra massive component of the universe, makes up 85% of the total matter. So basically everything, most of what is out there is dark matter. Obviously, because we don't know what it is, though, it's very like hard to pinpoint like what kind of, if it's a particle, if it's a wave. So WIMPs, which are stands for weakly interacting massive particles, is the most accredited kind of dark matter. It's just a one particle that is theorized that could be what dark matter is. And this is basically what LZ is looking for. LuxZeppelin is just this detector who's here at SURF, and that's what we're looking for. Yeah, so I think.
Mike kind of alluded to it. The reason I was put on the panel is I'm kind of the historian. So I've been with the project since kind of the design phase. And the rest of the panel up here has never seen a lot of the hardware that actually makes up the detector. So we sealed up the detector in early spring of 2021. So we sealed up the water tank. And so what you see up here, and I'll kind of turn around so I can point to some key things. So Olivia talked about dark matter, kind of what is the theory behind dark matter, what do we think dark matter is, but then there's how do we detect it and how do we find it. So the way that LuxZeppelin works is basically here in the heart of it, see right there, we have a large cryostat that holds 10 tons of liquid xenon. Xenon is a noble gas. It's a gas at room temperature. We have to cool it down to actually liquefy it. So when you think about 10 tons, it's also very heavy. So 10 tons is about 700 to 800 gallons. We're used to the unit gallon. About 700, 800 gallons of liquid xenon. It's at about minus 200 degrees Fahrenheit. So that's at the core. And essentially, LZ is kind of like an onion with many layers. The reason for that is we need to shield it from the world outside of it. So we're looking for minute interactions inside that liquid xenon. To do that, to see those, we actually have to shield it. Otherwise, we just gets lost in the noise. So when you look at LZ, you've got the cryostat, which is full of liquid xenon. Outside of that, you have these massive acrylic or plastic tanks that are filled with a material called liquid scintillator. So when particles go through it, it actually produces light as well. Outside of that, then this whole thing is in a 73,000 gallon water tank filled with about the world's purest water. So it's taken a long time to get to where we're at right now, and we've been running since essentially spring of 2021 was when we started all of our commissioning. We filled the detector at the end of 2021, and we've been running filled since. So a lot of hardware that you see, there's also a lot of hardware outside of it. So to make all this happen, we have cryogenic systems that move liquid nitrogen around. We have compressors. Chad will talk about this. So we actually circulate the xenon around, because not only do we have to fill it, but we also have to keep all of that xenon pure, because if we get impurities in it, that actually decreases our ability to detect dark matter. So there's a lot of hardware that will be talked about as we go through the presentation, and it all supports the main function of finding dark matter. So you look at this, and if you were able to look at the iPad out there and look at the scale, I mean, we're talking something that's about 5 feet in diameter by about 5, 6 feet tall. So it's a big object. All of that went down a shaft that the compartment we went down is about 4 foot by 12 foot. So we tried to fit everything we could in the cage that goes down, or the elevator. The stuff that wouldn't fit, we actually slung underneath. So we were able to get a little bit bigger, but everything still had to go almost a mile underground. So I'll turn it over.
Okay, so as Charles mentioned, so the heart of LZ is this big tank of liquid xenon. And the way that we go about detecting the dark matter particle is that, so if we imagine like a billiard ball example, which is kind of like the very basic example that we usually give, is that if you imagine like the white ball that you're using to hit the rest, you'll have the white one hitting one of the ones that you're targeting, and that ball, the one that you're targeting, will recoil back. And what this does, this is basically the very basic principle behind LZ, which is that if a dark matter particle comes in and interacts with one of the nucleus of the xenon, then it will create this recoiling nucleus of the xenon atom, and that creates light. So liquid xenon is a very, like, it's one of the best, well, it's the best element to do this, because it has this property that when energy gets deposited, it just sparks. And so what we do is that we have, so I have like this diagram here, which is, if I can make this work, oh yeah, which is kind of showing like a particle going in, and then you can see here that there's a spark of light, and then there's also, we have these two sparks of light, which are called S1 and S2. And those twos are basically the only thing that we need. We use that to reconstruct the event. And this is what the events actually look like. So this is really the data that we look at. So all our data is just composed of events which have pulses. So it's just like literally a line that tells us about like the time evolution of the detector, and we just have a lot of pulses. And we use these to reconstruct everything that happens. Now the issue is that actually there's millions of things that happen every day in LZ, because as Charles said, so dark matter is a very rare interaction. We're talking about like a few, if any, few events per year. So we really need to like understand everything that's going on, because it's not just dark matter that does this recoiling. Anything really that hits any atom in the liquid xenon will create this recoil and spark. So what we want to do is kind of like, imagine being in a very loud room and you're trying to hear someone whisper to you. If it's very loud, you're not going to be able to see it. So you want to kind of like filter out that noise so that then you're like ready to see the very tiny things that you're trying to see. And the way that we do this is by what we call cuts and background studies. So a cut is basically, well, what we do is that we apply a series of, we know what a WIMP interaction would look like. We have a certain amount of like criteria that we know like the interaction has to satisfy such that we can classify that as a dark matter interaction. And so what we do is that we basically do a bunch of, have a list of selection criteria that if an event passes, then we go on to the next one, and if it not, it gets rejected. So this is what like a cut would be. So usually the way that it would work is kind of like, oh, we have one condition here. Is it satisfied? Yes, no? Okay, if yes, we go to the next one, and we have a series of those. And then at the end of the day, we have kind of like our golden data set, which is kind of the ones that we're like, yes, this could actually be a dark matter candidate. The story is not finished though, because there is a lot of other things that like, there is things that look like dark matter that potentially satisfy the same things that dark matter would do. And the way that we go about addressing those is with background studies. So by background, obviously, we mean anything that's a background to the dark matter. So something that looks like it, but it's not really. And so, so part of it is, as Charles mentioned, is mitigating them. So for example, we're underground because there's this cosmic ray flux that comes from the universe, which is like kind of like bombarding our detector with a lot of muons and like things that like would spark in the detector, and we don't want that. So we go underground. We're 850 feet underground because we don't have those down there, because the rock is shielding us from that. We also have the water tank, who's kind of shielding us from all the external. For example, we are in a natural environment, so obviously the rock is got some radioactive components that emit gammas or things that could just spark inside it. So we have the water tank for this. And also in the diagram before, you saw like there's a lot of components, the organic scintillator that Charles mentioned, which also serves as what we call a veto. So anything that kind of penetrates inside it will spark inside that veto system. And so it will kind of be, hey, I'm not dark matter, because dark matter should not do that. Dark matter should only interact in the xenon at the core. But then whatever is left, we basically model it. So we have a big part of what the analysis effort in the LZ data is modeling all the background that we can see. And so basically the way that it works is that you use simulations, which is basically you create mock data for everything that would be inside your detector. And then you kind of try and model as best as possible so that when you have your final selection, you can kind of subtract everything that you've modeled. And in theory, everything that's left is your dark matter. So that's kind of the strategy that we go about finding dark matter. I think this is Julie.
Now you know what LZ is, what dark matter is, how we're going to do it roughly. We kind of want to take a moment to talk about who is going to make this happen, right? So big world-class experiments like LZ don't just happen in a void. There's people and resources that make it happen. And so in this case, LZ is made up of 250 collaborators. There's scientists, there's engineers, there's technical staff. We span a variety of disciplines. And then of those people, they were spread across 38 institutions. And you can kind of see on the side over here, all the different institutions, and they're kind of color-coded by what continent they're on. And I've kind of listed, there's, America, UK, Korea, Australia, Portugal, Switzerland. We're all over the place. And everybody who's collaborating, we are in real time, in real different time zones at all times. And we're kind of talking back and forth. And it's just this huge, massive collaboration at all times. And so kind of we're going to give a little profile about who we are and kind of what we do and how we ended up on this collaboration, right? So I'll start it off. I started out with a Bachelor of Science in Mining and Minerals Engineering. And then I actually went and took a detour and I worked in pharmaceutical manufacturing right out of college. And then I went back into mining engineering. So I spent some time actually doing designs for a dragline operation out in a coal mine out in Montana. And then, that kind of led me here because it took the two things that I am passionate about, both lab work and, kind of an industrial environment. And it kind of married the two, and I get to do both. And it's been this very fulfilling experience. And kind of my day-to-day is never the same. My title is an experiment support scientist. And so I get to leverage my engineering background, and I get a lot of hands-on with tools. I get to interact with data. I kind of make sure that the detector is kind of humming along and doing well on a day-to-day basis, and kind of just keep an eye on that.
So my background is I was born and raised in the area. Grew up, if you know where Alzada, Montana is. It's the booming metropolis of about 25 people. I grew up on a farm and ranch. I went to school to be a mechanical engineer, and when I graduated, I wanted to stay close to home so I could be involved with the ranch and being born and raised in the area. I love the area, so I actively looked for opportunities to stay close. When I got out of school, I worked in industry for about 5.5 years. Did a lot of traveling, kind of supporting plants and stuff. I was in the plastics blow molding industry. And so while I was there, I got a lot of experience in kind of control systems. So how do you take something that you need to do something mechanical with, how do you make that automated? So that was kind of my background. It's kind of funny, when I started this job, I knew nothing about what I was going to get involved with. Talk about taking chances. The people that actually hired me took a chance, and it was, so I've been with the Sanford Underground Research Facility for about 9 years. My roles kind of changed, so when I started, I did a lot of design, primarily in the liquid nitrogen handling system. So moving liquid nitrogen that's minus 320 degrees below zero. Did a lot of design work there. The insulating systems that keep everything cold. A lot of the controls work, so the sensors, and working with our controls group to actually get a lot of the different systems of LZ to work. So I did that on the design side, and I've been fortunate to actually was with the project through installation. So we worked with a large team to actually get everything underground, get it all assembled, and then transitioned into operations. And so all through the commissioning and the startup of the systems, and then kind of just getting into running it as efficiently as we can. And it has its moments, but for the most part, it works very well. And then kind of now my roles kind of change because kind of getting Chad, he's a new engineer that started with us, kind of transferring the knowledge and being engaged that way, not so much in the active day-to-day, but as problems come up, kind of getting into the mind of the people that designed it. So.
Yeah. My background is very shorter in the sense that I grew up in Italy, and then I really liked maths, and I just wanted to do something with it. And so I decided to move to the UK, and I did a bachelor in physics. And then I kind of discovered that I really liked particle physics and did a master's, and then just decided I want to stick with it. I wanted to keep learning, and so now I'm doing a PhD. So I'm starting my 3rd year of PhD now in London at Imperial. And yeah, so I'm here because So as part of our PhD program on LZ, it's kind of like there's an included experience abroad period. And because obviously I work on LZ and LZ is here, I came here and I've been here for 3 months. And I've kind of like been jumping around. Whenever there's something that needs help with, I will help. Obviously, everyone that's kind of underground is always there. So they have like their own system that they help with. While for me, it's more like I don't have something that's mine. So I just kind of help and whoever needs. And otherwise, I just keep on doing my work, which is just data analysis, which is kind of like what I was talking about before. But yeah, that's me.
All right, so I also grew up in the area, lived in Spearfish. So then I spent some time in the Air Force, where I worked as a machinist and a welder. Got to work on some cool aircraft there and go to some interesting places, as you could say. From there, I got an associate's degree in metals technology, and it decided, maybe I can do this school stuff after all. So I got a bachelor's degree in mechanical engineering from Montana State University, and ended up working at a lab there doing high altitude ballooning. So we'd fly kind of sensor packages and things and chase those all over central Montana. So it was a pretty cool experience. From there, I started a job as a manufacturing engineer with a company that did kind of large format metal 3D printing with lasers as the heat source. So it was kind of really cool technology to be around. They had a lot of aerospace customers, so we had a lot of really cool projects. But I was always kind of looking to move back to the area. I really liked growing up here, so I was watching the surf website every couple of weeks, looking for job postings to come up, and finally one did, and I got lucky. I kind of feel like I won the lottery a little bit. I never thought I'd be working on the world's leading dark matter experiment, and definitely never working on something so cool, so close to home. So I've been with surf now a little over 6 months, I think, and happy to be here talking with you guys.
Now I'm going to talk you through, we call this this presentation A Day in the Life of a Dark Matter Scientist, right? So we have some pictures, and I'm going to talk through kind of what it looks like to be us. What does a day in our lives look like? So Olivia and I, we go underground just about every day. And so this is kind of the underground experience. And so we start our day, before I have pictures, because we start it in the PPE room, so personal protective equipment, right? We get to the locker room, and we put on our coveralls and our hard hats and all of our stuff that you see us wearing in these pictures. And then we hop on a shuttle, a delightful 12-person van, and we all shuttle over, and sometimes there's 2 shuttles, we all get over there. And then this is the cage. You guys have all seen the cage that's outside, right? It's just the big elevator that takes us down. There's not a lot of us in it on this day, and I'm standing at the back of the cage in this picture, so you can kind of see my vantage point. And there's not a lot of people in there, but you can squeeze 29 of us in there. On any given day, there could be that many people. So we go down, takes us about 12 minutes, and then this is where we land at the 4850. This is out coming down the Ross shaft. The Yates looks different, but you can kind of see the top of the cage is right here, which means this whole space is just space. It's empty. But that's so we land in a pretty big area, right? And then we kind of walk into a smaller area, and then kind of trudge along. But then we actually spend a lot of time, you can't really see the motor in this picture, but our friend Lindsay is riding on the front of the train. So there's actually a little choo-choo that takes us most of the way across the level. And then before we get to the clean space, which you see there, we don't want to walk in there with all of our dirty boots. I mean, look how dirty those boots are. So we actually change our shoes. So we change our shoes, we take our coveralls off, we leave our hat, we drop our belt, and we just, become a clean human for the day. And then we live here. This is where a lot of our desks are. We're kind of along the side of this long hallway. They call it the common corridor. And then through these doors is where LZ actually is. And we start every day with the toolbox talk. And it's funny because there's actually no toolboxes in the control room. But we kind of talk about what the tasks are for the day. We have every functional piece of the experiment is represented, and there's functional leaders, and we kind of go through, and there's people who call in from off-site, and we go through what needs to be done for the day. And that's kind of what you're seeing here. This is just how we orient ourselves in the morning. And from there, we kind of launch in to the tasks for the day. And so kind of leading off into that, we're going to have Chad talk about some of the projects. And here's talk about this is because everything that we do on a day-to-day basis kind of comes through the engineers much of the time first. And so it's all kind of a lot of back and forth. There's stuff that we touch every day, and there's stuff that they touch when it needs a little bit more engineering.
Fair enough. So, I figured just to kind of give you guys more of an idea of what we do as mechanical engineers with SURF and LZ, just kind of talk about some of the projects I've worked on. So first up here, we've got a nitrogen generation system. You can kind of think of this as maybe a fancy filter. So we're feeding this compressed air from the surface. That'll come, down through tubing a mile underground to the Davis campus where this unit's located. It comes through that filter system, and essentially what it's doing is kind of grabbing those oxygen atoms and letting the nitrogen in the air pass through. So the end result of this is we end up with a tank full of ultra pure nitrogen gas, and we can use that gas to do things like purge the water tank or the xenon storage bottles and prevent any sort of contamination from getting in those. It's gonna save us some money, hopefully, and reduce our reliance on liquid nitrogen deliveries from the surface should those get interrupted in any way. That's all I had on that one. Yeah. So here we've got some photos of our xenon compressors. Charles talked about them a little bit. They're really at the heart of the LZ system at this point. They're circulating that xenon through the detector. And as you can imagine, with something kind of that integral to the system, there's a lot of scrutiny on these. The maintenance is pretty involved. So the two photos on the right there are just some maintenance activities taking place. And then the photo on the left is going to be one of our recovery compressors. So this is what will actually put the xenon back in its storage bottles at the end of the experiment. And as part of the maintenance on that unit, we need to remove the top compressor head. So if you look at that photo, it's kind of that big metal cylinder towards the top of the unit. And it weighs about 700 pounds, and my project has been trying to figure out how we're going to pick that up. So due to the xenon piping that's been installed above it, there's only about 5 inches of clearance to make that lift. And nobody sells something that'll do that. So we're going to design and build our own. And so it's been a kind of unexpected project, but a fun one nonetheless. The last stuff here I was going to talk about is maybe more conventional engineering stuff. So, we have all the fun one-off physics type things happening, but we also have heating, ventilation, and air conditioning. So all of this is critical to the LZ experiment itself and the Davis campus as a whole. They need fresh air, chilled water, things like that. These are, general commercial units. You can find these anywhere in, say, an office building or something like that. But once you put that a mile underground in a dirty and humid environment, and then you run it 24/7 for years on end, suddenly that becomes difficult to maintain. So we work hand in hand with our infrastructure technicians trying to solve any problems that may come up with these systems in order to feed the Davis campus with all of the air and electricity, sewer, water, anything it needs. These photos are just some of the piping that leads into the actual Davis campus to kind of for scale. So that's all I've got.
Another big part of operations is calibrating the detector. So we don't do this all the time, but it is something that kind of happens on a schedule relatively. And so first I'm going to tell you what calibrations is. The basic concept is if you have a scale, you know that I could take this and put it on a scale, and one scale will tell me it weighs 200 grams, one might tell me it weighs 204 grams, another one might say 207, right? So they're all right, but there's kind of a correction factor that should be applied to find out which one is the most right. And so the way you do that is you calibrate a scale is really simple. You just take something of a known weight. You know that this weight weighs 200 grams exactly. And so then you know that, okay, this known weight comes on the scale. So this one's 4 high, this one's 7 high, and this one's just right. The Goldilocks principle, right? So we do the same thing to our detector, but it's a little bit different because it's not weighing things, right? It's measuring a signal. And so the way we calibrate our detector is we take objects of known activity, something that's going to have a signal output that we know what it should be. And then we measure what the detector sees is the very, very general explanation for what it is we do. And the way we do that is we have 2 very general categories that sources kind of fall into, right? There's the kind that we either put it into the detector, it's an object, kind of an insertion sort of situation, or it's an injection situation. Like when you have medicine injected into your veins, it goes through your whole circulatory system and it kind of is through the whole system. we have sources that we inject that way kind of into the circulation of the detector itself. And we do this periodically, and it gives us readouts and data. And then people like Olivia take that data and they find answers.
Yeah, so we mainly, as Julia said, we mainly calibrate like in these two ways. And also in these two ways, like there's two main reasons why we calibrate. So the first one is, well, both of them, it's kind of like, so we know how our detector behaves and we can kind of like basically understand how it works, and we can make the most out of it to find dark matter. So there's two main reasons why we do it. So the first one is that because we have like a detector that has some spatial size, you want to be able to kind of like reconstruct where your events are happening. And so there's some types of calibration sources that we use, which basically what it does is that, kind of like Julia said, you have one known activity or something that you know exactly how it behaves, and you spread it uniformly in the detector. So you circulate it such that it's everywhere. And then you kind of look at how the response of your detector changes in space. And that basically tells you how each single point in the detector behaves slightly different. And the reason we do this is both because you want to have a good kind of like spatial reconstruction, but also because the detector changes over time. Slightly different situations might lead to slightly different correction factors that you have to apply to your data. And so this is one of the like first reasons that we do it. The second reason is a bit more related to the background discussion that I was having before. And so before I gave you the billiard ball example, so we have a WIMP, a dark matter particle that comes and strikes a nucleus. Now, depending on what kind of particle is coming in, the interaction can actually happen with the nucleus or with an electron in the atom. So here, I have the little atom, and the WIMP could come in and like hit the nucleus, or it could come in and actually hit the electron. And that would mean that the electron is actually the thing that's recoiling. And those two things are quite different. And so because we know that a WIMP is supposed to create what we call a nuclear recoil and not an electron recoil, then what we do is that basically we do as much, the two calibrations that we do is that what we call neutron calibration and electron calibration, basically. So we use neutron sources, so we kind of like bombard our xenon with neutrons, and we see what the response of the detector is. And then we do the same with electrons. Sometimes we will, well, actually the electrons, we don't really bombard them. We like kind of like put sources in that will create electrons. But so when we do this, basically this is what we see. This is a very like complicated plot, but the bottom line is that in orange, you see all the events that happen when you bombard it with neutrons. And the blue one is when you kind of have electrons in. And so you can see that these populations are very, very different. And the reason we do this is because in this space, you would expect your dark matter to be here. And so if we know what it looks like, we can kind of calibrate our detector to be like, we really want these bands to be as defined as possible, so that whenever we will see the dark matter, we can check that it's actually where it's supposed to be. Because maybe an electron will still like look like a WIMP, but because it's here, we know that it's not. So that's kind of like the bottom line there. And so I guess the final question is, have we found it? The answer is no, unfortunately, not yet. But that doesn't mean that like we're failing, because I mean, I have this little doodle here, which I guess is showing like the reason that we didn't find it is not because it's not telling us that it's not there, but these kind of detectors kind of like the more, because we're talking about very, very few interactions every year, you kind of want to be operating as much as possible, because maybe you haven't found it yet, but you will find it in the next year or so. And so, I mean, I have these doors, meaning, we haven't found it, but this just means that we have like opened some of the doors, and some of the doors are still closed and we still don't know. So for example, if you look at this other plot that I put there, like the message here is that this line here, which is what from our latest results that we actually came out like 2 days ago publicly, basically what we're saying is that we've looked here above this line, it's not there. So we have to push it down. We have to go more down. We have to search more for it. So there's more to explore. If we find it, it will be good. If we found it, we want to explore it more. So we'll keep on running. Finding it is not the end of the story. And if we don't find it, we'll just have to, keep on going. And at some point we will. So, yeah.
kind of the timeline to kind of expound upon what Olivia said. So the timeline for our project is decommissioning late 2027. So we've actually got an extension. So we're actually planning to run basically up until the end of 2027, and then we'll finish up decommissioning, removing everything in 2028. So we've got a number of years left to keep searching, and also like for Chad and I, keep everything running. So we initially planned for about 5 years of runtime, and so we're going to go way past that. So
I guess we're gonna open up the questions.
Testing 1, 2. There we go. So, audience, what questions do you have? We have one to start with right back here.
What happens if in 2027 you still haven't found it?
Maybe a little louder.
Well, yeah, there's already plans actually for a next detector. So these detectors is actually the one after a series of smaller detectors. So we're kind of going bigger and bigger. Like Lux Zeppelin is from Lux and Zeppelin, which were two different experiments that then kind of like got together and made the bigger one. So actually we have, well, LZ is the leading detector, and then we have Xenon and Ton, which is the other detector, which is a very similar technologies. And we're actually already like kind of creating a collaboration to make the next generation experiment. So if we don't find it, we'll just keep on looking for it with the other detector. And if we do, I mean, detector, as I said before, if we do it last minute, for example, we still want to study it. So we still need something else. So yeah.
Each version of the experiment, and we build on it, and we look in different places, and we kind of explore different parameters as we go.
Do you have an estimated mass for the particle?
Well, we're talking giga-electron, giga, is that giga in English? Giga-electron volts. Well, if you actually look at this plot, you have kind of like the WIMP masses on the x-axis. We're talking like 10, like the most, we're talking like few giga-electron volt to a few tera-electron volts, but we don't really know. It's just kind of like why we're looking for it.
Okay, I'll try and combine my questions into one. So to kind of start, if we don't, do we know a lot about the composition of what dark matter is? And you said that when particles collide with xenon, it creates light. So we know what elements exist on stars because we can measure wavelengths of light coming at us. So on a particle level, can you do the same thing? And if so, if we don't know, if we haven't found the dark matter, how do you know it's there? And then you have all this data. So at what point, how much of this is kind of a data science, computer science problem? And what can you kind of speak to that side of things, like where you send data out, do people analyze it in different ways? Like how are we looking at processing the data differently? So if we don't know what it is, how do we know when we find it? Can we do any type of, I don't know, spectrometry type, something similar to that? And then, can you speak to the computer science, data science side of this?
Did I get that?
Like, yep, you're the data lady.
Yeah. So,
thank you for asking.
well, okay. So, sorry, what was the first question?
If you don't know, if you haven't found it yet, how would you know when you find it?
Well, so the way that data now, so before, obviously, like, it's a very complex process because, as I said before, we use these cuts, we use background analysis, but then at the end of the day, we don't really do any kind of like subtraction. Like there's not really a way. All the things that we measure are kind of come with what we call an uncertainty. So, like when you measure something, you're not 100% sure in it. So basically, the way that like the analysis, like the final analysis work is that you will have like a certain amount of data, a selection of events that you think look okay, that they look okay. These all look like they could potentially be fine. And then the way that it works is that we do like a statistical analysis. So we have a background model, which is kind of like modeling all the backgrounds that we think would be there. And then the way that it just works is that there's as I said, like a statistical model that basically tells you, based on this amount of events and on this background model, do we see an excess? Is there something more that is not accounted for by the background model? If there is, then that's your hint that you're seeing something. But if you don't, then you're kind of like, it's this no WIMP interaction result. So it's like, so for example, this is what has happened with the past two results. So we look at all the data, we have a background model, and when we look at it, it is consistent with it just being background. So if we see it, basically the way that it would work is that you kind of would see an excess, and then you would investigate it and run for more time, and then eventually the excess would be enough that you can actually say, yes, we saw it. In terms of characterizing it after we found it, that's a bit more of a tricky story, because LZ is able to reconstruct a lot about an event, so you can reconstruct the energy. But obviously, so for example, knowing, like, even if you do, at the point when you do see an axis and can say with certainty that you found it, you don't have the event that's dark matter. Like, you will never be able to pinpoint which one of the ones that you see is, or maybe you would at some point, but so it's kind of like, it's quite tricky as a, so you can't really do like spectroscopy like you would do with stars. There was another question.
Like can you speak to the data analysis, computer science aspect of this? Like,
yeah.
What exists in that side of things?
Well, so really, the way that it works is that, I mean, we obviously have like the operation side of things, and then we have the data analysis side of things, which is what I'm most involved in, and most of the like grad student and kind of like academic side of the collaboration works on. And the way that it works is that usually we have like groups that will be taking care of certain aspects. So we will have people that will focus on some certain background. I, for example, work on certain xenon isotope decays that happen that like are a background. And so basically it's kind of like a joint effort. Everyone's kind of like coding up all the time. You basically, is a data informed thing. So the way that we do it is that we look at the data and we just analyze it. And by analyzing it, we kind of like learn a bit more about the detector, and then everyone's kind of doing their part to make, at the bottom line, the main thing is the background model. But then there's also a lot of like data quality. You want the data to be as good as possible. So even if an event would be fine, maybe like it happened in a weird position, and so the correction there is not as great, and so you want to cut that out. So there's a lot of work going on. It's obviously mostly computational work. Like, the operation side of things is kind of what's going on here at SURF, and then remotely there's an army of analyzers that are kind of like looking at data all the time. Yeah. Yep.
Awesome questions, awesome answers. Your questions don't have to involve answers in giga electron volts or advanced data analysis. So you can ask any question you want. I want to encourage everyone to be able to ask anything. But great questions, great answers.
I always understood that a third generation xenon detector was going to be limited by the neutrinos. And so is there a way that they're thinking about getting around that limit of neutrinos, that when you get bigger than LZ?
Does anyone know that one? I don't know that one.
Well, yeah, what we call the neutrino floor is not like, you can't really mitigate it. Right. Basically, it's limited by that, but it's really a long way since we reached that. So the point is kind of like, so the neutrino, for everyone, basically what this is that, as I said before, we have a lot of cosmic rays that are coming from the universe, and these are all shielded by the rock. And however, there's still what we call neutrinos, which is actually what Dune is going to be studying, that don't interact with matter. Like, they interact very little. And so basically, one of the main challenges of as we push more down and down in this plot here, at some point we reach what is called a neutrino fog, really, which is basically meaning at some point we're going to reach a realm of this space where there's going to be these events of neutrinos that we're going to start seeing. And those are, because they have a signature similar to dark matter, it means that if we're not going to be able to distinguish between the two. I'm not 100% sure whether there's like some kind of effort to mitigating that, but kind of my understanding is that the aim is to reach it, and then, yeah. But we are a long way from it, so there's still a lot to go.
If we get to the neutrino fog with Gen 2, that would go a long ways towards negating Gen 3, but if we don't get there yet, there still is, we could sweep lower. So
I have one more question back here, and then I'll come to you.
I was wondering, like, is the dark matter like uniformly distributed throughout the universe, or is it like clumpy?
It tends to clump.
Okay.
But as I said before, because so the observation for dark matter is that it's kind of like one of the main things is that it kind of like agglomerates at the edges of a galaxy. And so what this means is that essentially what's happening is that as we're rotating in the like around the sun, we're basically moving through this dark matter halo. And so we have this constant stream of dark matter particles going to the Earth. Like it's not dark matter is coming to us, it's more like we're moving through it, and so we're seeing this flux. But it does tend to like kind of like agglomerate in big like chunks.
So is there anything like, so if it is almost like a drag being created in a dark matter field?
Well,
so
yeah.
Is there like some kind of a, like suppose it was not there, then this would be the, change in the dynamics of the planet, and if it is there, then this is what we are observing. Is there like some sort of like that kind of a?
I think the main thing is that like you can't really observe it by a different like it barely interacts with anything, so it wouldn't like affect, like for example, it wouldn't have like a drag like, I don't know, stars or like some kind of hot plasma would. But actually one of the main other observation, like proofs of dark matter, is what is called the bullet cluster. Basically, this was something that was observed in the 90s, I think, that basically they saw this merger of two galaxies. And so obviously, as you mentioned, these two galaxies merged, and so there was a drag of the matter that was inside these. But then what happened was that when they kind of like did the gravitational spectrum, so kind of like seeing where the mass of the two galaxies is, there was no drag. So the two dark matter halos kind of like crossed each other without even like seeing or doing anything to each other. And that's also one of the proofs. So dark matter it doesn't interact really. So, and which is why it's very hard to find it and see it.
So this kind of matter, was it like created in the beginning, like at the beginning of the universe, or?
I think we don't know. Well, we think that it would be like, there's like, for example, the WIMPs, which is the candidate. One of the motivation why we think they're a good candidate is because there's like the way that their characteristics and their mass would be able to explain, like them being created at some point at the beginning of the universe would be able to recreate the kind of like equilibrium that we see right now in the universe. So for example, the cosmic microwave background, I don't know if you've heard about that, but it's just this like remnant Big Bang radiation. So yes, but also it could be that it's something different, and then I'm not sure.
Thank you.
Well, I'm just wondering, you had all of the people who are participating throughout the world. Does anybody else have the LZ, or is LEED the only place with an LZ thing? The machine, yeah, the detector.
One LZ detector.
But there are a number of detectors that use similar technology. Olivia mentioned there's one in Italy, Xenon Anton. So it's another really competing experiment that's looking for dark matter using xenon. There's one in China at Jingping, which is another laboratory called Panda X. And then those are the three large xenon detectors. And then there's other detector types that are also looking for dark matter too, using different technology.
Usually, sorry, go ahead.
But to Charles's point, there are other detectors that are similar to ours, but ours is the most sensitive one.
It's
you can see that on
yeah, exactly. You can see them all.
And xenon on the curve.
We have the fastest race car on the track right now. Is that right?
Yeah.
That's excellent.
It's kind of like it's true that because there's so many universities, as Julia mentioned, we're kind of all working already thinking about what's next. And so many of the university actually have lab like in school that, like for example, my university, we have a lab there and we have like a mini LZ. And so what we do is that it's literally this big. And we kind of work on it, and we'll test different like detectors, we'll test different technologies. So there's kind of like tiny like efforts, R&D effort to like kind of like make it better for the future. But LZ is one and only.
Well, and also LZ was kind of, in some ways was assembled at different locations around the world, and all the pieces were kind of sent here for final assembly and like kind of to be built into the final detector. And that same process is ongoing for future generations of similar experiments that pretty much at any given time, somewhere at a university, they're building something that's probably going to go into the next generation.
What other questions do we have from the audience? I've got just a couple back here. I'm going to come back and then I'll come to you, sir.
Just wanted to know, is an offshoot of this to try to figure out different energy sources available to us nowadays?
The classic, what is dark matter good for?
As in like finding dark matter after? Well, this, like for now, I feel like this is more like science for the sake of science, research for the sake of research. We see, like, I think it's the call of a researcher to kind of like try and understand as much as possible of the universe. And because some things don't add up, we want to look for it. But I wouldn't say that, like, who knows, maybe at some point we will find a way to harness it somehow, if we find it, when we find it. But for now, there's not really, like, we're not doing it because we want to use it for something. It's more like there's this big question mark that's there in our physics model for the world. And so we just want to fill that kind of like gap for now, I think.
We got to find it, detect it, and then characterize it before we can figure out exactly what it's good for.
People often ask that question of why dark matter? So what good if we find dark matter? What good does it do for us? And if I may interject, I point back to the theory of electromagnetism, that is all of the technology we have today, radios, cell phones, microwaves. That was 1866. James Clerk Maxwell, a brilliant young Scottish mathematician, could see the theory of electromagnetism, and it's the basis of all technology we stand on. So the discoveries that these folks are making are really about multi-generations potentially ahead. And it's also beautiful in that sense that we're exploring the unknown. So if sorry for letting me interject, but it's a wonderful thing to be involved in, all of us here in the room.
Can you describe the statistical models you use to look at or analyze the possible candidates?
I can try. Well, I think so what we use is called profile likelihood ratio, but it's not really meaning anything in the sense that I think the way that it works usually is that, as I said, we do these background models. So we will, for example, like we know that there is one specific component that's, for example, radon, which is everywhere. And we know that like there's progenies from that like end up in our selection. There's stuff that comes from that decay chain that is there. So we try to model it as much as possible. We use simulations. We kind of use like the knowledge that we have of a certain source. And then the way that it works is that we kind of have what we call like guesses. So we will, by doing this analysis of the data, we will come up with guesses of what we think is the number of events of this kind that we would see. And then we will have a certain amount of data, which is the entire data set. Like, for example, in the latest, it's like about 1,000 events that pass all the cuts and selections that we do. And then each of the sources and background that we will have a number. So like, I don't know, radon, we think there's going to be like, I don't know, 100 events. And then this other source is going to be 50. And we go on and on and on modeling them all. And then basically we just give this all to a nice code that runs and does some kind of like minimizing statistical analysis, and then basically gives us the best fit parameter. So it will try and make it such that based on your initial guesses, it will kind of like jump back and forth between all this number to find the best combination of numbers possible that then is explaining your data. And if you see kind of like a number that makes sense, usually it will be something like if you have like 1,000 events and your background model is saying like 999 plus minus 5, then realistically you are within range of it being just background. There's a lot of complicated stats which I don't really understand very well, but that's kind of like the basic spiel, I think, that I understand.
Great stuff. We've got time for just one or two more questions. I got one right back here.
Is your published results, are they available to the general public?
Yes, they are. This is the, well, we have 2 results out. One came out in 2022. And then one came out, well, we announced them to the world in August, but it actually came out publicly the paper came out 2 days ago. And it's actually, if you Google this, that's the title and you'll find it.
Okay. All right. Wait, one more question? Do I have time for one more?
So the whole search for dark matter began as you observed the rotation of the galaxies. They weren't behaving as they properly should. Besides dark matter, what other theories out there explain this rotation that doesn't make sense?
I think there's some modified gravity things that are out there. I'll be honest, I'm not a theorist, so I'm not really sure. I know that there is a lot of different theories. Like there's a lot of people that think dark matter is not the answer, but it is the most accredited one. Like it's the one that most of the people in the physics world agree on. So I think gravity, like modified gravity, is one of the main ones, but I'm not sure about any other.
Well, we take great pride at the Sanford Underground Research Facility at advancing world-class science. And I think this panel and all of LZ exhibits that to the max. And so let's give a round of applause for our panelists. We do have some parting gifts. We have some parting gifts over here we're going to give to you. So stick around. Thanks for that. And our next